In this example, we are asked to replace this system of forces and moments with a single force. So the first thing that we're going to do is break each of these forces into its orthogonal components aligned with the x and y axis. And so we can kind of inspect this first of all and see which forces we need to work on here. So we need to obviously break A here, the 100 newtons at the origin, into an x and y component. So we'll just draw on a placeholder x and a placeholder y. We'll need to work out components for the 70 Newton force B. The same for C. We note that C and B form a couple because they are two forces of equal magnitude. They point in opposite directions and they're parallel. And we'll work out a component or set of components for the 50 Newton force D. Right, so rattling through each one of these in turn, we'll start with force A. Alright, so our x component is going to be 100 times the cosine of 70, and our y component is 100 times the sine of 70. Okay, so we have 34.2 newtons and 94 newtons for the x and y components respectively. We can move on to force B. Alright, so the x and y components are 29.6 and 63.4 newtons respectively. And so we notice as well that because B and C are a couple, we've obviously worked out the x and y components of C as well. They'll just be equal magnitude and opposite direction to the components for force B. So we can move straight on down and look at force D. Alright, so now that we've worked out our components, let's just draw them onto our main diagram. And also let's not forget that we have a moment at E and a moment at F. So we're going to have to take those guys into account as well. Right, let's start off by evaluating the sum of the moments, so working out the moment effect of all of these forces and moments. So we're taking or evaluating the sum of the moments about the origin. So we'll just say the sum of the moments about the origin is equal to, and again I haven't stated it here, but the sign convention here is that clockwise moments are positive. So let's consider the force at the origin first. Well, we'll write it down for completeness, but it doesn't generate any moment effect because the horizontal and vertical component, they pass through the origin, and so they have no lever arms. Our lever arm is 0 about the origin, but we'll write them down, as I said, just for completeness. So we'll say 94 newtons times a lever arm of 0 meters plus 34.2 newtons times a lever arm of 0 meters. So they were the contribution of the components of force A, which clearly are 0 and 0. All right, let's look at force B. So the horizontal component of force B, the 29.6, is going to have a lever arm of 2, and it's going to generate a counterclockwise rotation, so it'll be a negative moment. And the vertical component of 63.4 has a lever arm of 6 and will also generate a counterclockwise moment, a negative moment. And so we can represent those in our moment equation. All right, let's add in the contribution from C. Okay, well, C, the horizontal component. Now, about the origin, it will have a lever arm of 3 meters, so that's 29.6 by 3 meters, and it's going to generate a counterclockwise moment. And the vertical component of 63.4 will have a lever arm of 5, and it will generate a clockwise moment. Okay, so let's add those in next. All right, and then let's add in the contribution from D. So D, its horizontal component of 47, will have a lever arm of 3 meters, and that 47 newtons will generate a clockwise rotation or a positive rotation. And the vertical component of 17.1 has a lever arm of 6 meters and will generate a counterclockwise rotation about the origin. All right, now we can't forget the contribution of the moment at E, which is a positive moment, so that's going to just be an additional 20 newton meters added to our expression. And then the moment at F is counterclockwise, and so that will be a negative 75. So we'll plus 20 newton meters and negative 75 newton meters. And of course, that's for the moment at E and the moment at F. All right, and so we can evaluate all of that. And it ends up that the sum of the moments about the origin is a negative 35.7 newton meters. And the negative means that it is a counterclockwise rotation. All right, next we can take the sum of the forces, some of the horizontal forces. Take or evaluate the sum of the horizontal forces. So again, we're assuming, if I don't say it, we're assuming that forces acting to the right are positive. All right, so what are we going to have? Let's have a quick look up here. So we've got the 34.2 for A. We have the negative 29.6 for B, plus 29.6 for C, and negative 47 for E. So we can just evaluate those. And so the sum of the forces in the x direction is equal to a negative 12.8, and the negative is indicating that we have a resultant force acting to the left. And then the next step is to work out the sum of the vertical forces. So let's have another little look. So we've got the 94 for A, 63.4 for B, a negative 63.4 for C, and a negative 17.1 for D. And that all evaluates out to 76.9 newtons, positive number indicating that the resultant force acts upwards. Okay, so the next step is to combine those horizontal and vertical components into a single resultant force. All right, so we said the horizontal component was a negative 12.8, so that was a 12.8 acting to the left. We said the vertical component was 76.9, positive number, so it acts upwards, so that's something like that. And so the resultant vector would look like this. So let's just call that F sub res, label this guy Fx, we have a number for him, and label this guy Fy. Alright, and so the other thing that we need to specify is the orientation. Now I'm choosing to specify the orientation with respect to the positive x-axis, and so if I just sketch it on there, our positive x-axis is going to be that guy there, and so the angle alpha is going to be this guy. You can specify the angle of orientation with respect to whichever axis you like once you're clear about the axis or the reference axis you're using. I'm going to say the magnitude of F res is equal to the square root of 12.8 squared plus 76.9 squared, which is equal to 78 newtons. And now we want alpha. It's going to be made up of two parts, right? So it's going to be 90 degrees to get me around to here, and then whatever angle this is in here. So I'll say alpha is equal to 90 plus tan inverse of 12.8 over 76.9, which makes alpha equal to 99.5 degrees. Okay, so we're nearly there. So the question actually asked us to replace this system of forces with not a force and a moment like we had previously, but we got to replace it with a single force. And so we can't actually directly add a moment. The question that we're being asked precludes us from doing that, and so we have to generate a moment some other way. So the question becomes, how can I generate an equivalent moment? So I've got a force to work with, and I got to somehow use that force to generate the equivalent moment of a negative 35.7 Newton meters. And so the predicament we're in is that we need to generate a moment of negative 35.7 Newton meters with F res. And so the only way we can do that is by shifting F res so that it doesn't pass through the origin. We got to give it a lever arm. And so the two easy options we have here are we could shift that force, we could move the point of application of F res along the x-axis, or we could move it up along the y-axis. They're the simplest options we have. Option one, if I'm just going to sketch them out very roughly here, would be to shift the point of application along the x-axis, because previously we were also applying a moment, and so we were able to apply our force at the origin because we could generate the moment we required by directly applying a moment. But in this example, we're not allowed directly apply a moment, so we've got to generate that moment some other way. So if I just roughly sketch on, imagine that was my x-y axis. We now need to shift our force, something like this, along the x-axis. And if we visualize what its components are, it's got a vertical component like this, a horizontal component like this. This was 12.8. This was 76.9. The resultant was 78. And so now in shifting it along the x-axis, what have we done? We've generated, let's go with red, a lever arm for that vertical component. So now the vertical component has a lever arm, let's just call it lambda. So that's one option. The other option is we could take our force and we could shift it vertically. Now also, before I draw on the other option, remember it's a counterclockwise moment I have to generate, right? It's a negative 35.7. And so that means that if I was over here now, if I was generating my moment by shifting along the x-axis, I'd have to shift it in the positive x direction, because that way the vertical component here would generate a counterclockwise moment about the origin, right? If I shifted my force to the left, right, in the negative x direction, well then the vertical component would be over here somewhere, and about the origin that would generate a clockwise moment, and I don't want that. I want a counterclockwise moment, and so I have to shift to the right. And so let's actually finish that out before we move on to our other option. So I'll say in this case the moment is generated by the vertical component, and so the only question really becomes what is the lever arm? How far do I have to shift that force? What's lambda? Well, I know a moment of 35.7 is going to be generated by a force component of 76.9 multiplied by some lever arm lambda, and we can solve for lambda equals 0.46 meters. And so in that way I could generate an equivalent system. So this is my equivalent system that has the exact same force and moment effect as the original system we started off with, provided we take our resultant force and we move it along the x-axis 0.46 meters. Okay, so the other option was to shift it along the y-axis. So again, it's a negative moment we need, and we're generating that negative moment with the horizontal force component, which acts to the left, and so that means the force would have to be shifted, I should say, vertically in the positive y direction, because now it's this component of force, which we said was 12.8, has got to generate the same moment. So let's call the lever arm here beta. The vertical component obviously doesn't generate any moment because it passes through the origin. So in that case, the lever arm beta would be the moment I'm trying to generate, 35.7, divided by the force that I'm using to generate the moment, 12.8, and so I'd have to shift vertically upwards 2.79 meters. And that would be another alternative equivalent system. So either or option, let's call this option A and option B, either one is an equivalent system for the system of forces and moments that we started out with here. All right, and that wraps up that one.